minutes after. But, all right, I think it's not like this is making dings or something when people join, so at least that part got set up correctly. So I think we can start. Just let everyone know I'm going to record the part of the actual talk, and then I'll turn off the recording, and then we can lock the meeting after that, as we filter in for the discussion parts of this. So anyway, welcome to Rohit's final defense. Rohit, you want to take it away?
Absolutely, thank you. So first of all, thank you everyone for joining this virtual defense. I know it's in the middle of the day, right at lunchtime, and most of you left important work to join this. So I really appreciate you coming and attending the talk. Let me just yeah. So my talk today is on model checking large design spaces, and it describes the research work that I did as part of my PhD dissertation. But before I talk about model checking, let's take a step back and look at what is a design space, because we really want to understand if we want to model check that. So let me answer that question with a simple example that involves aircraft. So given the problem of airspace allocation, we want to ensure that there is no loss of separation between aircraft in any possible airspace scenario. A scenario in an airspace can consist of two aircraft that can only communicate with the ground controller, or it can also contain two other modern aircraft that can communicate with each other as well as the ground controller. In another possible scenario, we can have four aircraft that communicate with each other and also with the ground controller. And in another different scenario, we can have four aircraft that can only communicate with the ground controller. Besides having the different aircraft combinations, we can also have options to configure how much information is shared between all the airborne agents. And for example, in the case of a potential loss of separation, which airborne agent or the ground agent is responsible for resolving a conflict? Either it is the aircraft which can only communicate with the ground controller, is it the ground controller itself, or is it the modern aircraft which can also coordinate among themselves as well as the ground controller? Overall, there are a lot of design choices to consider to ensure there is no loss of separation between aircraft. So coming back to my question of what is a design space, in a nutshell, it's a set of possible design choices for a system. Now let's look at what I mean by design space exploration. So coming back to my example of airspace scenario, we have the requirement that every possible airspace scenario must meet certain design requirements over all the possible behaviors of agents in an airspace. Simple examples of requirements include that there is no loss of separation between aircraft. And in the case of a potential loss of separation, the aircraft can actually detect that loss of separation and perform some mitigation measures to avoid the potential loss of separation. It is the goal of the system designer to find all combinations of design choices that satisfy each of these required design requirements. So design space exploration is a design time analysis technique to evaluate all the possible design choices exhaustively and make sure that every design choice meets certain specifications. More and more complex systems these days, they are modeled as design spaces. And the primary reason to model a design space is to perform comparison between different design alternatives of the system with varying design choices and requirements, to eventually narrow down to a final system design. So that would be the design which would actually go into production or for further analysis. The formal verification techniques like model checking, they can aid system development by performing a thorough comparison of all the possible design alternatives with respect to the design requirements. So in the problem of model checking design spaces, we now have a set of models that represent the different design alternatives and the set of different properties that express system requirements. It is important to note that every property might not hold for all models, as we can have some properties which are specific to certain design choices. The different properties and the models, they're evaluated using a model checking tool to return verification results for every model property pair in the design space. The goal of this dissertation work was to make model checking for these design spaces more scalable. Since design space model checking involves multiple models and properties, we achieve our goal by optimizing and adapting the model checking workflow for multiple models and properties. There are several other practical verification tasks that involve multiple models and properties. So all the work which we do in this dissertation equally impacts all of them. A typical task is that of functional property verification, in which we have one model that has to be checked against several properties. So we have the problem of one model and multiple properties. Another task is that of regression verification, in which every design update leads to a different model that is to be checked against several properties, including new properties that may have been added after performing the updates. So every time we perform a new design update, it leads to a new version of the design that has to be verified against the property. Then there is the highly prevalent verification task of equivalence checking, which tries to prove two designs equivalent by tying their inputs together and checking equivalence between intermediate design points and outputs. Every such equivalence that is established between the design points is an individual property that has to be proved, and proving the overall equivalence between the two designs often entails checking thousands or even millions of properties. Our contributions to improve model checking of multiple models and properties can be broken down into 4 verticals. The first vertical, that is design space reduction, focuses on reducing the number of models and properties that have to be model checked by finding all the intermodel relationships and property dependencies. The second vertical of incremental verification customizes model checking algorithms to learn facts about the design space when checking a model, and then reuses the learned facts when checking the next model in the design space. The third vertical of property grouping finds a group of similar properties that can be checked together to maximize the reuse of learned information. The fourth and final vertical of parallel orchestration provides a massive scalability boost by optimizing the parallel verification of multiple models and properties. So let's start with the first vertical, which is that of design space reduction. And in the figure, every time I move to like a new vertical, I try to emphasize in the red box as to what part of the model checking workflow we are trying to optimize. Now, before we do design space reduction, the first problem that we had to solve was how to actually model a design space efficiently. So in the classical method of modeling, every design choice leads to a separate model. However, this classical method does not scale when we have a large number of design choices, which can end up with a lot of different models, and then maintaining models across design updates becomes intractable for big designs. We propose a more scalable and maintainable method that models every design choice as a parameter to a meta model. So let me explain this with an example. Consider a simple transition system with 3 states, S0, S1, and S2. We can now introduce a Boolean parameter P1 that models a design choice that enables a transition between an existing state S2 and, let's say, a new state in the transition system S3. So if P1 is set to true, the transition between S2 and S3 is enabled. If it's set to false, there's no transition from S2 to S3. Similarly, we can have another parameter P2 that can model a design choice that enables a transition from state S2 to another state in the transition system S4. We call this resulting transition system with parameters a combinatorial transition system, and we present theory that allows us to reason on that in our papers. The different combinations of configurations for the parameters P1 and P2, if we set it to true or if we set it to false, each unique combination for the parameters leads to individual models in the design space that have to be checked against design requirements. So now we can model efficiently this large design space using a CTS with parameters, and to use a more technical word, like every projection of parameters, it leads to an individual model that has to be checked against the design requirements. In principle, a combinatorial transition system model can represent thousands of models under different parameter configurations. So as the first step in a design space reduction technique, we automatically try to find dependencies between these parameters, which in turn is equivalent to finding the intermodel relationships to reduce the total number of models that have to be checked. Then each model in this reduced set of models has to be checked against several properties that express system requirements, as well as several design choice specific requirements. Our design space reduction technique automatically finds some implicit property dependencies at runtime to dynamically reduce the number of properties that are checked per model. After model checking this reduced set of model and the reduced set of properties, the verification results for the reduced number of model checking runs are unpacked to give the model checking verdict, including the translation of counterexamples across models for all the models and properties in the original design space. Let's briefly look at how our D3 algorithm, which is a design space reduction algorithm, reduces the design space along 2 dimensions. So the first dimension is by finding all the dependent parameters to reduce the parameter configurations, which in turn reduces the number of models. And the second dimension tries to find dependencies between properties to reduce the number of LTL properties that have to be checked per model. Let's look at an example to see how the D3 algorithm reduces the number of parameter configurations. So assume that we have this combinatorial transition system with 3 Boolean parameters, P1, P2, and P3. And the setting of each of these parameters enables or disables a certain transition in the CTS. So a unique setting of all the parameters, P1, P2, and P3 leads to an individual model with transitions enabled or disabled between the states. And this is an individual model that corresponds to a valid design choice or a valid design alternative. A different parameter setting leads to a different valid model in the design space. And for the Boolean parameters P1 to P3, every unique combination would eventually lead to a total of 8 models that have to be individually checked against all the design requirements. And the 8 models, they represent the overall design space that is modeled using the CTS-MP. But if you look closely, you'll notice that the last 4 models, they're exactly the same. So even though they were generated by different parameter configurations, the resultant transition systems representing the individual models, they are identical. So this gives us an opportunity to reduce our overall verification effort in model checking the design space. So in this set of 4 similar models, we only have to check one model and then just apply the results for that model to all the other models in that similarity set. Visually, it's easy to see that we have similar models, but if the CTS is extremely large, finding such similarity can be extremely challenging. So our D3 algorithm, it automatically finds such dependencies to generate a minimal, and the point to note is minimal, so it guarantees minimality on the set of models that need to be checked to ensure that eventually when we unpack the results, we would have the results for all the models in the design space. Now let's look at how D3 reduces the number of LTL properties to check. And it does the reduction by focusing on finding the semantic dependencies between properties. So to give you an example of what I mean by semantic dependencies, let's say that we have a model M and it's a model over 2 variables, P and Q. And then we have 2 LTL properties, phi1 and phi2. So phi1 expresses that the variable Q, it holds in all possible states of system M, whereas phi2 represents that variables P and Q, they hold in all possible states of system M. Now, if we were to model check property phi2 with respect to M, and we get the result that yes, model M satisfies phi2, which means both P and Q, they hold in every possible state of M, then without even checking property phi1, we can conclude that phi1 also holds for M. And the same holds for the contrapositive of the statement as well. And if such a situation happens, we say that the LTL properties phi1 and phi2, they are dependent. Similarly, I could have another property phi3, which expresses that variables P or Q, they are true in all states of the system. Now, if property phi 2 holds for a particular model M, then without even checking property phi 3, we can automatically conclude that it holds for model M as well. And we say that phi 2 and phi 3 are dependent. Now, these are simple LTL properties, but as they get more complicated, knowing and learning these semantic dependencies becomes extremely hard. Like, property is usually expressed at the LTL level. We need to run some analysis to actually figure this out. So the D3 algorithm uses efficient LTL satisfiability checking to establish these dependencies offline. So it implements this as a pre-processing step to establish the dependencies between properties, and then uses these stored dependencies at runtime to dynamically reduce the number of properties that are checked per model. So D3 is a very efficient pre-processing algorithm, and I emphasize on the word pre-processing because we did not make any changes to a model checker. This was mostly, we have a representation of the design space in a formal model, and we are trying to work. And it provides an efficient way to start into base time in working with models and properties, which might not be required to do the entire design space exploration for a design space. We can definitely reduce it. So D3 finds the minimal set of parameter configurations to guarantee that, okay, we're only checking the minimal set of models, and it finds the dependencies between all the LTL properties to dynamically reduce the properties that are checked for individual models. The great part about D3 is that it works with off-the-shelf model checkers. If we have a suitable way to model a CTS in a given modeling language of choice, we can use D3 for our advantage. In our work, we extended SMV models, which are models written for the new XMV model checker, with parameters that could be enabled or disabled by preprocessor directives. We evaluate our D3 algorithm on several large design space case studies. And the figure shows results for one such case study with 1,620 models that represent NASA's air traffic control systems design space. So model checking the design space with D3, that is represented with the green line in the plot, is considerably faster than the traditional methodology to check models individually, that is represented in blue. And it gives us a median 4.5x speedup. All the other lines in the graph, they represent how we can build up from individuals. So first, by reducing the set of models, so that GenPC, it gives us a significant boost. And the ultimate boost is actually received when we find all these property dependencies. And we notice that for this specific NASA air traffic control system design space, so we had around 1620 models. Each model was checked against around 300 LTL properties, but D3 was able to reduce the design space by almost 54%. So it checked less than 1,000 models, and the number of properties did not exceed, I think, more than 100 properties a model. So there was a significant reduction right there. So design space reduction is extremely critical for overall scalability of what's to follow. We do not want to waste time in checking models or properties that are not actually required for design space exploration of the design space. The D3 algorithm, it achieves this by automatically reducing the design and using an off-the-shelf model checking tool to verify the different models for the design space against the properties. So although D3's pre-processing is extremely powerful, we get significant reduction in the size of the design space, the model checker that we use, it still has problems. It has to reset and start from scratch every time it checks a new model. So in the next vertical, we try to optimize this incrementality across model checking runs by enabling information learning and reuse. So before I proceed with the next vertical, I just wanted to see if anyone has any questions on this.
I have a question. So your examples you have here of saying essentially a property phi 2 whatever implies phi 1. So if I verify phi 2, I don't need to check for phi 1 anymore.
Correct.
The examples you gave are essentially probably I look at the LTL or whatever property, and I can say, yes, of course, phi1 implies phi2 for any model. So
Right.
it's completely independent of the particular model.
Right.
Can you do more than that? Maybe you can answer at the end, but that I just wanted to understand. So right now, your examples are all model independent.
Right.
Okay.
They are.
I will ask you the detailed question later. Then I just wanted to clarify this for now. Okay.
Sounds good.
All right.
Okay, so moving on to the next vertical of incremental verification, we now look under the covers of a typical model checking tool. So we move from our pre-processing algorithms to, okay, let's look inside a model checker and see what we can optimize. So when we are generating all the different models for a design space, we observe that different models which are generated by parameter configuring the combinatorial transition system, they are related. And they're related in the sense that the different models, they have overlapping reachable state spaces. And if you recall my example with that 8 models for a combinatorial transition system, several of them had overlapping reachable state spaces. The individual models which we generate after parameter configuration, they are checked sequentially for the design space. But because we are checking them sequentially, every time the model checker gets a new model, it resets and restarts the verification from scratch. But since we know that the models in the design space are related, it made us ask the question that, can we reuse some information learned by checking a previous model to really optimize our future verification efforts? So let's see this through an example. So let's say that I have a set of related models, M1, M2, M3, and M4, and I have a safety property phi that is to be checked against each of the models. The diagram represents, it's a Venn diagram that represents the reachable state spaces for the 4 models, M1 to M4, and then it represents the safety property phi as a set of bad states. So ideally, the state spaces for each of the models should not be intersecting with the bad states if the property phi is to hold for a particular model M. So let's say that the model checker first verifies M1 with respect to phi, and that's the M1 is the part in green. And it sees that, okay, the state space of M1, it does not intersect with phi, and then it automatically concludes that, okay, property phi is satisfied for model M. Now, when the model checker moves to model M2, ideally, traditionally, it would just reset and then start exploring the state space for M2 from 0. But we don't want to do that because M2 sort of contains the state space of M1. What if we had an algorithm that allows us to verify only the new reachable states that are added for M2 and completely reuses what it already knows about M1? So this saves us significant effort. Like we spend so much effort computing the state space for M1, why not just reuse that effort for M2? And a model checking algorithm like this, it would compute the new reachable state spaces in M2. It would notice that, okay, it intersects with the bad states and then conclude that, okay, M2 does not satisfy phi. So this was our aim to like generate and develop an algorithm that actually does that. So our algorithm is called Fuse IC3. It comes from like frame reuse. It will be clear why it's frame reuse in a few seconds, but it extends the bit level IC3 algorithm to support efficient incremental verification. So Fuse IC3 works as follows. So given a model M and a model N, we have to verify both the models against a safety property phi. So Fuse IC3 would first verify model M with respect to phi. When Fuse IC3 is verifying model M, it computes this frame sequence R, which represents the reachable state sequence, reachable states that can be reached in up to I steps. So for example, R1 represents all the states that can be reached from the initial states in 1 step. R2 represents all the states that can be reached in up to 2 steps. So it's important to note that R2 contains all the states of R1 as well, because it's in up to 2 steps. Based on whether the property phi holds for the particular model M or not, if it holds, IC3 would compute an invariant. So invariant is an over approximation of all the states in the system model M. And if the property phi does not hold, then IC3 would, fuse IC3, it would return a counterexample trace that shows the exact execution of the system starting from an initial state to a state that violates the safety property phi. Now the goal of fuse IC3 is to compute a similar frame sequence S for model N, but instead of starting from scratch, it should be able to reuse what it computed for model M and model M in terms of the frame sequence or the invariant or the error trace. So let me walk you through a high-level overview of how this actually works. So fuse IC3, it always maintains this internal state, which is the frame sequence for the previous model it checked, and then the invariant for the previous model if the property held for that particular model, or it could be the invariant for like the model before that, or an error trace, which would be a counterexample if the property did not hold. But it just remembers the last known information for each of these three information artifacts. So now when it moves on to model M, it has to compute the frame sequence S for N. So initially, since frame sequence 0 would essentially be the set of initial states, it makes S0 equal to the initial states of N. Now the goal of fuse IC3 is to be able to compute this frame sequence S1 that represents the states that can be reached in up to one time step for model N, but instead of starting from scratch, reuse R1 to fill that purpose. So we want to be able to compute this S1 using the information which we already have in our internal state. So as the first step, fuse IC3 does this very query efficient SAT checks, which essentially is saying that does the existing R1, which I have in my internal state, does it contain all the states that can be reached from the initial states of model N? If the SAT solver says unsat, which means, yeah, this definitely holds. In that case, we can just pick up R1 directly and make that equal to S1 because, yeah, we wanted that to happen and it satisfies the high level invariance that we want to hold. The situation becomes a little trickier when it does not hold. And the reason it would not hold is when there are some states in R1 that are actually missing, but they are reachable from S0 in one transition step. And now this is the beauty of the fuse IC3 algorithm. So whenever this assertion check fails, it tries to repair R1 hat by adding in enough states to R1 such that the new R1 hat that we get contains all the states that are reachable starting from the frame sequence S0. And it does this in a very query efficient SAT methodology. And once we have R1 hat, we can replace S1 with this new R1 hat. And we do the same for all the other frames in the frame sequence S for model N. At any given point of time, if two frames become equivalent, then fuse IC3 concludes that, okay, property phi holds for model N. This essentially means that we have found an invariant that is the set of all, the over approximate set of all reachable states, and it does not intersect with the bad states. So yes, property phi holds for model N. Otherwise, if it finds an error trace, which is a trace specifying that we have a state and that is a violating state and it can be reached from an initial state, then fuse IC3 can conclude that property phi does not hold for model N. Once fuse IC3 is done verifying N, it updates its internal state with the frame sequence S, which was recently computed. So now that becomes the last known frame sequence. And then based on the result of the model checking, it either updates the invariant I or the error trace. And then it prepares to receive the next model in the design space. Now the performance of fuse IC3, it's very much dependent on actually how we check these models, like what order we check them in. And it is easy to understand that, okay, if we are checking these similar properties in order, in like a certain defined order, we can actually maximize the amount of information Fuse IC3 uses. But to answer that, like we have these few basic questions. So first, like how do we actually find all these similar models and properties? And like a more fundamental and basic question, like as to how do we actually define similarity? So intuitively, if I say similar, then it means, okay, maybe I'm mentioning like semantic similarity, like the design behaves exactly in exactly in the same way, or like designs behave similarly. But measuring this semantic similarity, it's actually very hard, and it cannot be done without consuming any verification resources. And we might just like slow ourselves down by spending so much time computing this semantic similarity. So we don't want to do that. So that is out of the question. However, we do have static design data that is just measured without doing any verification, and it's readily available and can be used to measure similarity. So for models, it is the model representation, which can either be in the form of like a bit level and inverted graph netlist, or it can be in the form of clauses, which eventually get sent to a SAN solver. So it's a CNFI's netlist. And for properties, we have cone of influence that actually represents a subset of the model that may be required to like prove a property. So now that we know that we have this static information, which we can use, okay, to some extent to compute similarity, given this static data, how do we actually find similarity? So one would think of like hashing for finding identical models and properties. So hashing works great when you want to like find identical hits, but traditional hashing functions, they actually fail for similarity, because a good hash function is the one in which for any like minor change in input, there is like a massive change in output. And we don't want that. We actually want the inverse of the statement, that for minor change in the input, there is a minor change in the output. We want something like that. So this made us look into some like data mining literature, which made us, after which we ended up using and adapting this technique called locality sensitive hashing, which is a hashing algorithm to actually measure similarity between text documents. So to give you an overview, locality sensitive hashing works as follows. So if I have these 5 documents, D1 to D5, and I want to find similarity between them, locality sensitive hashing hashes these documents using several hash functions and then organizes the hash signatures into these different bands. Once the hash signatures have been organized into bands, documents which have identical hash signatures across bands, they are considered similar. And the amount of hash functions you have in a band, or the size of the number, or the number of bands, that is an algorithmic parameter that can actually be used to control the levels or the thresholds of similarity. So we thought, okay, yes, we can sort of adapt this for doing similarity checks between models and properties. But what does it mean, like the document in terms of a model, or like a document in terms of a property? So to answer that, like if you think about models, the model representation in the form of the netlist can actually be used as a document. So because a model checking algorithm would receive a netlist, and we can just hash those different netlists and get all these different hash signatures. And for properties, all the support variables that are actually there, the support variables by that I mean all the registers and inputs in the cone of influence of the particular property, they can be organized into like a document, into like a structured document, and then we can use hashing to find similarities between the cone of influence of properties. So locality sensitive hashing, it gives us a very good heuristic technique, although it's offline, because I'll talk about why it has to be offline later, but it gives us an efficient partial ordering on models and properties, such that the models and properties which we group together, and if we use Fuse IC3 on it, Fuse IC3 can actually use more information across the different model checking runs. So to summarize this, so Fuse IC3, it reuses the already verified reachable state spaces it has for previous models in checking all the new models, and it reuses these IC3 frames that are stored and then repaired using very efficient SAT algorithms across multiple model checking runs. So Fuse IC3 gives us a very efficient way to perform incremental verification, and adding in this partial ordering with locality sensitive hashing significantly boosts the performance of Fuse IC3. And since especially for like regression runs in which there are minor design updates, and if I can have multiple updates, the partial ordering allows us to put an order on those models and then efficiently check them using Fuse IC3. So we evaluate Fuse IC3, which is shown with the blue line in the plot, with a state of the algorithm for incremental IC3, which is shown in the red line. And a typical state of the art, but a non-incremental algorithm for IC3 that is shown in green on the same NASA air traffic control system design space, which had 1,620 ADC models. And as you can see from the plot, Fuse IC3 is considerably faster than the existing state of the art for an incremental IC3, and much, much faster than a typical IC3 with like no incrementality built in. And it's successfully able to achieve a 1.75x speed up compared to a state of the art version of an incremental IC3. So this actually really exemplifies the benefits of information reuse across runs. And it helps us achieve significant like verification scalability if you're able to decide a perfect ordering of models and properties and then reuse them across the different runs. So incremental verification, it really pushes the limits on the size of the models that can be verified using model checking. And if you think of it, I can start with like a small model, learn everything about that model as reachable state spaces, and gradually the model builds up. But it's very much possible that had I started with like a big model in the first place, I might not have been able to verify that. But this incrementality, it gives it a very good advantage. However, the efficient reuse of information across models, it is sensitive to the ordering of models and properties. If for some instance, like I check a model first and then another model which is completely different, Fuse IC3 would actually be slower because it's spending so much time in repairing all these reachable state spaces than to just check the new model on its own. So although our technique of locality sensitive hashing helps to some extent, it still requires expensive offline analysis for computing that cone of influence and then performing that property grouping. And since it requires using these several hash functions, although it gives very accurate results, it is time consuming. And it works well for the NASA ADC models, which have like fewer properties, but it does not scale as well as much as we want for like for designs with like millions of properties. So this brings us to my third vertical of property grouping. But before I move that, do we have any questions up until now?
Just clarification, in your Fuse IC3, when you had your example of the frames R and then Ri and then the frames Si, is Si a superset of Ri? Or do you make it become a superset of Ri?
That's right. Eventually it will become after the repair.
Okay.
Because some states were missing from Ri, so we are just adding in more states into that.
So, but if the two have nothing to do with each other, as you just said, then essentially you're making the set large for no good reason.
That's right.
Got it.
Right. So moving on to the third vertical of property grouping. So the goal of property grouping, as we saw with like Fuse IC3, is to like partition properties that have high structural affinity, and all the properties in a high affinity group we want to be able to check together. And cone of influence, which is the design logic on which a property depends, or the part of the design on which the property depends, that gives us a very good measure. So that gives us a very good measure that gives a very good way to measure structural similarity. So to give you an example, if I have three properties, P1, P2, and P3, just computing the cone of influence and deciding how the cone of influences overlap, we can determine that, okay, P1 and P2, they are structurally similar, so should be grouped together. And while P3 has a disjoint cone of influence, it should be grouped separately from P1 and P2. However, computing these cone of influence for all the properties is extremely hard to like perform quickly because it has quadratic complexity in the sense that for every property, we need to traverse the netlist again and again. And since we are doing repeated traversals of the design, if the design is huge, it's a severe bottleneck to compute this cone of influence. And this is something which we faced when we were using locality sensitive hashing on ordering all the properties. So in the iterative method of computing cone of influence, so given 3 properties P1, P2, and P3, I would pick property P1, traverse the design once, and compute the cone of influence for P1. I would then move on to property P2, do a traversal again, and then get the cone of influence for P2. And then similarly, I would do for P3. However, if you notice this iterative method, it requires like repeated traversals of the design again and again for every property that we want the cone of influence for. And as a result, it does not scale if I have like millions of properties and very large designs. We use a more scalable method. So in our method, as usual, we would compute the cone of influence P1 by traversing the netlist once. But when we move on to P2, we only compute the non-overlapping cone of influence for P2 and directly reuse what we know about P1. And this is achieved by using these efficient graph labeling approaches, which give us like linear runtime. And eventually, when we move on to P3, we can repeat the same process. But because of this efficient graph labeling to compute all the cone of influences for P1 to P3, it only requires one traversal of the entire net design, and it's a linear traversal in the size of the design, but it's extremely scalable because given like thousands of properties, our computational complexity does not depend on the number of properties, but only depends on the size of the design space. Oh, sorry, not of the design space, size of the design. So given this linear method to compute cone of influence, our next goal was actually to optimize how we store this cone of influence information in memory. So in our work, we store the cone of influence for each property as an index support bit vector over all the support variables in the design. So if an indexed bit in the bit vector is set to 1 for a particular property, it essentially means that the corresponding variable for that particular index is in the cone of influence of the property. If it is not in the cone of influence of the property, that particular index in the bit vector is set to 0. So given this representation of cone of influence as bit vectors, we had several optimizations to how we actually store and operate on these bit vectors. So we merge all the support variables which form strongly connected components in the design into individual bits. So that helps us reducing the size of the bit vectors in memory. And for efficient computation, we performed frequent garbage collection for all nodes, which we have computed the cone of influence for and are no longer required to compute the cone of influence for the property. And just topologically traversing the design, and by that I mean starting from the input towards the properties, it helps us get rid of cone of influence, which we compute for intermediate nodes, and clearing it out of memory. So it gives us like significant advantages. So comparing our method, which is the support vector method, to the iterative method of cone of influence computation, which requires several repeated traversals, on a large collection of benchmarks, we get a greater than 100x speed up. So this was like a severe performance bottleneck for Fuse IC3 to find groups of properties, which we solve in this version of the work. So our next step was to use these stored bit vectors to actually do property grouping. So we perform property grouping based on cone of influence. So given these properties P0 to P9, so it's a set of 10 properties, initially every property is in its own singleton group. So as the first step in our property grouping procedure, we perform structural affinity grouping, which merges property based on similarity between the cone of influence, or based on similarity of the structural cone of influence, that is information which is statically available to us. However, it might be the case that although two properties are structurally similar, or for instance, they can have identical cone of influence, they may end up having different semantics. And by that, I mean the proof or counter example for a property only depends on a subset of the design logic in the cone of influence. And this subset is actually different for the two properties that were grouped together. So as the third step in our property grouping procedure, we add in the ability to perform semantic partitioning of high affinity properties by learning high affinity properties by learning all the semantic information in an abstraction refinement loop. And this is a more dynamic approach because we started with structural groups before running any verification, and then semantic information starts getting collected after we perform localization abstraction. So we are consuming verification resources to perform this semantic partitioning. And semantic partitioning, it's actually extremely useful for very large high affinity groups, for which it might be the case that if I were to just break that group into smaller subgroups, they are easier to verify. But since we grouped them together, they had high affinity, they are just harder to verify. So given the cone of influence representation as bit vectors, the problem of grouping properties based on cone of influence, it reduces to finding properties with similar support bit vectors above a configurable threshold of how we are defining similarity. So in principle, there are several techniques in classical clustering which allow us to do that. But for our purposes, because we wanted property grouping to be extremely quick and spend most of our verification effort in doing the actual verification itself. So the existing classical clustering techniques like k-means or k-medoids, they require quadratic comparison between bit vectors for each property and tend to be extremely slow for our purposes. So to mitigate this problem, or to mitigate actually the quadratic performance slowdown we get because of classical clustering, we use a 3-level approximate clustering algorithm. So the 3-level approximate clustering algorithm, it works as follows. So given an initial grouping of properties P0 to P9, and each property is in its own singleton group, level 1 grouping performs, it merges property groups that have identical support bit vectors. And this means that two properties, if they end up in the same group, they have 100% affinity. They have an identical cone of influence, and they should definitely be checked together. However, we can make a trade-off. Like, there are several verification tasks which can often tolerate small dissimilarities between properties, which leads us to level 2 grouping that tries to merge properties based on the strongly connected components in the cone of influence of the properties. So if two properties share a large strongly connected components, our grouping procedure ends up grouping them together. However, for verification tasks, if we require more control on property grouping, we then introduce another level, level 3 grouping, which merges properties based on the Hamming distance between the different support bit vectors. But although it's using Hamming distance, it does this without ever computing the Hamming distance between between any pair of property. So I'll talk about level 3 grouping in like my next slide, but this was like, I'm very proud of this algorithm. So after like generating all the different high affinity groups, the groups have a provable lower bound in terms of what is the pairwise affinity between each property in a group. And we proved that we would never generate a group that has a lower than 3t minus 2 affinity between properties. The different properties that get generated, they can either be checked concurrently, which means we can check all the properties in the group at the same time, or the individual groups, they can be refined using semantic partitioning in an abstraction refinement loop if that particular group is very hard to verify. So although like our grouping technique is sound, it would never end up grouping properties that are dissimilar and put them in the same group. It is lossy in the sense that it may fail to group some high affinity properties, but that is the trade-off we are willing to make in terms of speed versus accuracy for a property grouping algorithm. And locality sensitive hashing, it gives us a very accurate property grouping, but it trades off speed. And over here, we sort of changed our goal to get good approximate clustering, but not give up, which gives us good accuracy, but not give up on speed. So let's look into how the grouping algorithm merges based on Hamming distance by avoiding the pairwise comparisons and Hamming distance between the different support bit vectors. So as I said, we don't want to do exact Hamming distance calculation between pairs of properties because it leads to a quadratic performance slowdown. So in our procedure, given a bit vector v for a particular property, so the bit vector contains a sequence of zeros and ones, we generate a normalized bit vector using a map, and using a map that assigns every 16-bit segment in the bit vector to a unique index. So this map that we generate, it's essentially mapping 16-bit numbers to unique indexes, and it can either be generated on the fly, which means by that I mean during the verification run, or it can also be generated just once offline, since the map can actually be reused across different property grouping runs. So it's a one-time cost to generate this map. Properties that map to identical bit vectors, identical mapped bit vectors, can then be grouped together and form a level 3 group, which has a provable bound on affinity. And if you notice, like, we are just picking up bit vectors, reading them 16-bit by 16-bit, getting a new map bit vector, and then the problem just reduces to comparing the hash signatures of the different bit vectors. So never in our algorithm, we actually do a pairwise comparison. But the workhorse of this technique is actually the map that we generate, which is mapping 16-bit numbers to unique indexes. So we evaluate our grouping algorithm on several hardware verification benchmarks from the model checking competition. And the reason we move on to like the model checking competition and not the NASA air traffic models is because we actually wanted to test this out on benchmarks which have like thousands of properties now, because we are aiming for like scalability now. So each benchmark in the model checking competition set of benchmarks, it contains between like hundreds to like thousands of properties. And all of these properties, they are in the design after simplifying the design by by logic synthesis techniques, which remove certain redundancies and perform simplifications. So as you can see, for like the most difficult properties, the grouping procedure, it takes less than 10 milliseconds to group thousands of properties. And as we move on from level 1, level 2, level 3 to eventually performing all the 3 levels together, there is not a lot of time lost. Like, we still achieve all the overall grouping across the 3 different levels that can be controlled by the user in less than 10 milliseconds. So this was, again, like a very much faster than locality sensitive hashing, because that would, even with like around like 1,000 properties, it would still end up taking like a few minutes. But this was like a great method to reduce the time span. So our property grouping algorithms, they partially order the properties in a big property set to maximize the amount of information that can be reused between different property runs. And it performs requirement grouping based on the cone of influence. So it can either be cone of influence, which is statically available in the form of the structure of the design, or it could be the cone of influence that is learned by performing abstraction on the design in a localization abstraction loop. The different property groups, they are verified. The different properties in a group, they are verified concurrently. And then the different groups, they can actually be checked in parallel. And if a group is too large, that is, it contains a lot of properties, we can optionally refine that group in a semantic abstraction loop. Our property grouping leads to extremely fast multi-property verification. But besides that, it also helps us in achieving smaller abstractions for high affinity properties that are localized concurrently. And this was a very solid impact of this work, because before we had an efficient grouping procedure, there was actually no way to perform counterexample guided abstraction or proof-based abstraction on a set of properties, just because if we end up abstracting 2 properties that are structurally dissimilar, we end up with these disjoint logic subsets that are just harder to verify. So this actually forces a localization abstraction to work on like guaranteed high affinity subgroups. So this was, I'm very proud of this again. So in terms of like end-to-end verification speed up, verification with group properties it's almost always faster than doing verification with like no grouping at all. And as you can see from the figure, it gives us a median 4.3x speed up. And although it was known that grouping really benefits multi-property verification, before this work, there wasn't an efficient algorithm to perform property grouping. All the other approaches, they were either doing expensive offline computation or using these off-the-shelf clustering methods, which would often take like hours to like work with thousands or millions of properties. And this gives us a very efficient way to perform property grouping and reap the benefits of multi-property verification. So coming to an end for this, so property grouping, it significantly boosts end-to-end verification performance. It enables the model checking algorithm to reuse the effort expended to prove a property in a high affinity group when proving all the other properties in the same group. So it spends some time checking a particular property, and when it moves to the next property in the group, it tries to reuse what it did for the previous property. And then all the different groups that have to be verified, they can be run in parallel for maximizing verification throughput or maximizing the number of verification results that we can get in per unit time. So this leads me to my fourth and final vertical of actually optimizing parallel verification for large design spaces. And before I do that, any questions on this?
So Rohit, a time check, it is 1:59. If you can keep that in mind while you go through the last bit of your contributions.
Got it. Okay, moving forward. So our property grouping procedure, which I talked about, it partitions properties into high affinity groups for parallel verification. All the different groups, they can be independently verified in parallel. And it is often the case that the number of parallel resources available for a particular verification task, they're known beforehand. State-of-the-art verification tools, they utilize different strategies for parallel verification of property groups. So there is the strategy of property partitioning that distributes groups across all the parallel workers. But these workers, they're identical in the sense that each of them runs the same version or the same strategy to prove all the properties in a group. There is the other verification strategy of strategy exploration, in which all the properties, they are sent across the different parallel workers, and each parallel worker, it runs a different version of the algorithm. However, workers have the ability to group properties locally within a strategy. So although these two different strategies, they help in parallel verification, the typical usage of these parallel strategies, there is significant resource wastage, and there is so much redundant computation happening between workers that, if avoided, can really maximize our verification throughput. And instead of thinking about these strategies in silo, in this part of the work, we try to focus on optimizing complementary property partitioning and strategy exploration so that both go hand in hand and help us give the maximum throughput. So we identify problems with a typical usage of these strategies, and then all the problems that we identify, we propose optimizations to mitigate them. So let's briefly look at a few of these problems. So the first problem is that of resource underutilization. So given a set of properties P0 to P9, which are 10 properties, we would use property grouping to generate these 3 property groups, G0, G1, and G2. In a property partitioning strategy, a partition manager will receive these property groups and then dispatch them to the available compute nodes. And the compute nodes can either be threads or processes, or it can even be like a very large computing grid. So in this example, we had 3 property groups, and the 3 property groups, they're dispatched to 3 out of 5 available nodes. So while the 3 nodes that receive a group each, they start working on verifying the group, the other 2 nodes, they are simply idling. And these were resources which were available to us, but because of the property grouping, we are not actually able to use them. So instead, like just to make things simple, we could have just like picked up on the 10 properties, distributed them or divided them into like pairs and then split them across the 5 compute nodes, and then every node would have been utilized. So although like this sounds tempting, we do not want to lose out on the benefits of checking high affinity property together. And if we were to just break up a group into 2, we might lose the requirement of like having a high affinity group. So this leads us to an improved property grouping algorithm that optimizes the previous property grouping algorithm to ensure that all available compute nodes, they are fully utilized. So starting with all the properties in singleton groups, the first check that we do is that if the number of properties is less than the number of available workers, then we can just return all the properties, because now we have at least one worker to work on like individual property, and we do not need to perform any grouping. We're already using the maximum amount of resources we can. However, if it is not the case, then we continue with our property grouping procedure, and at any particular grouping level, and if any particular grouping level generates fewer properties than available workers, we preempt our grouping procedure at that particular level and then perform this rebalancing to distribute the generated groups after that grouping level and ensure that all the workers are utilized. So for example, if after level 2, the number of groups, I end up with fewer groups compared to the number of workers, then I would call the rebalance procedure. Otherwise, I would proceed with level 3 grouping. And now rebalancing is the major workhorse of this improved property grouping algorithm. So to quickly overview group rebalancing, it takes as input all the property groups G after a particular level. It takes the amount of nodes N, or the parallel workers that we have, and it takes the level at which the grouping was preempted. And it's only run when the number of groups are fewer than the available workers. So if grouping was stopped at level 1, then we iteratively pick the largest group G from the set of groups, and we just halve that group G into G1 and G2. And this is simple because we know that all the properties in the group there had 100% affinity. So whenever we halve the group G into G1, G2, we would end up with 2 groups that have 100% affinity. And we keep doing this for all the groups in our original set until the point we have more groups than the number of available workers. And at that point, we return the groups. The situation is different when grouping actually stops at a level other than 1. So if it stops at level 2 and 3. So for that, we iteratively pick the lowest affinity group G in our original group set, and we roll back the group G, this group G, into 2 groups, G1 and G2. This rollback procedure tries to split the group G into 2 groups, but also ensure that they're high affinity. And it does this not by doing pairwise comparisons, but by using these efficient approaches which build on the hashing approaches I talked about in the previous section. So the 2 groups, G1, G2, that get generated, the algorithm ensures that they have higher or equal affinity than the original group G. And we keep doing this up until we have more groups or equal groups than compared to the number of parallel workers. And at that point, we return the groups. So coming back to the problem of resource underutilization. So we had these 10 properties, and which were generated by 3, which were put into 3 groups, and then 2 nodes which were idle. We can use our improved property grouping algorithm with rebalancing to roll back those groups G1, G2 into smaller groups, albeit maintaining higher affinity guarantees. And since now we have 5 groups to verify and we have 5 nodes to use, each node works on a separate group, and we guarantee that we'll have full utilization of all the available parallel resources. And at the same time, guarantee that we are not losing our high affinity guarantees. Another common problem is that of idle processes and workers, in which some compute nodes, they start idling while the other nodes, they continue to solve hard to prove property groups. So going back to my example with 10 properties and 3 groups, let's assume that the 3 groups, they are being run on the 3 available compute nodes. And each of the compute nodes, they try to prove the properties in the group. Now it may happen that the groups G0 and G1, they are easier than group G2 and can be proved easily by two of the compute nodes. So once they are proved, the two nodes which were working on G0 and G1, they start idling while the third continues struggling to prove the group G2. So from the perspective of the overall verification throughput, we might just be better off to like just break up group G2 and then send all the different properties in G2 to the available compute nodes. However, again, we do not want to first preempt the worker that is solving group G2 as it may be very close to a solution. Maybe it would take like just another minute more to prove. And secondly, we do not want to lose the benefits of high affinity grouping. So to mitigate this problem, our rebalancing procedure, it allows us to enable to split, it enables us to split the unsolved group and dispatch the rebalanced group across the idle nodes while still continuing the verification of G2 on the node that was working and maintaining the benefits of high affinity verification. And it might be the case that because we broke up group G2 into smaller subgroups, the verification of these smaller subgroups is actually easier compared to the original group G2, and the two nodes, they can easily verify these smaller subgroups, which would eventually end up speeding up the overall verification process. There are several other problems that affect parallel verification strategies. I will not discuss them, but just list out the contributions. So there is the problem of redundant computation across workers, which results in several like result races as to which worker finishes the task first. So we introduced this iteration order heuristic, which allows us finer grained control on the order in which groups are iterated for individual workers. The other problem is that of overall progress inhibition in a worker, in which a particular worker just gets fixated on like solving a hard property, and it might be the case that several easier properties might follow. And if we were to prove the easier properties first and then come back to the hard property, it might be easier to solve the hard property as well. So our controlled repetition heuristic, it enables these fast, lossy, and aggressive verification strategies that allow us to preempt the verification of a particular group, pause it, move on to the next group, and then come back to the group at a later point in time. Lastly, there is the problem of time degradation on a hard to prove group, in that even after several repetitions of control, or even after several controlled repetitions, we are still not able to prove that particular group. And it might be possible that although the bigger group is hard to prove, the smaller subgroups, they are much easier. So we have this decomposition heuristics that decomposes these hard to prove property groups into subgroups by using the rebalancing procedure that I discussed. So to measure the impact of like how all the different like parallel verification strategies and like the new improved property grouping algorithm we evaluate our techniques in a redundancy removal portfolio. And redundancy removal is the core solver strategy that is used in equivalence checking. And the reason we focus on these type of benchmarks is, again, we want to be able to really show like scalability on designs which have like thousands of properties, and we can really boost their scalability. So we designed a 6 process. So we tried to limit, okay, we are coming up with a new portfolio. Let's have like a reasonable 6 process portfolio, which is like a state-of-the-art localization portfolio. And we focus on localization because it's a known technique for solving all the non-inductive miters for redundancy removal. So the 6 process localization portfolio, it's generated by mixing the different types of localization strategies, which are enabled by a heuristic. So that's fast, lossy, and aggressive. So fast, lossy, they would preempt a particular group that is hard to prove, move on to the next, and then eventually come back to the first group. Whereas in the aggressive strategy, we would just continue working on a particular group until we have actually proven it. So it's aggressive in that sense. And we differ all the different levels at which we perform the grouping across the 6 processes, and how we utilize these combination of heuristics across the 6 processes. So we did this entire like wide study on what is the best combination of all these fast, lossy, aggressive grouping levels and heuristics to come up with this actually extreme, like it's like I would like the best state of the art or something like that localization portfolio. And this localization portfolio, it optimizes like both strategy exploration and property partitioning. So we compare this portfolio with other state-of-the-art portfolios for localization abstraction, in the sense that, so BEST represents our 6-process state-of-the-art localization portfolio. BASE represents a portfolio in which we're not doing any grouping at all, and we are using no heuristics. So this is, I would call it like state of the art before we had efficient property grouping. And then BASE plus G, I would call it state of the art after we had efficient property grouping in 2019. And then BEST minus D and BEST, they essentially differ in if we end up with a hard to prove group, are we decomposing it into smaller groups or not? So that's the difference between them. And as you can see, like our improved property grouping algorithm and all the different parallel verification strategies, they give like a 3x speed up compared to existing approaches. Another good advantage of utilizing all these different strategies and heuristics is that we get uniform work distribution across processes. So it's not that across the 6, one process is significantly solving more properties compared to the others, and some of them are just idling. So it uniformly uses them throughout, and it maximizes the throughput that we get out of the verification task. So optimizing parallel orchestration, this was like a final hammer blow on this entire effort that like significantly boosts the scalability of model checking for large design spaces. And by large, I mean now we can have several models which are being checked by Fuse IC3, and then property grouping on like millions of properties, which can significantly boost performance. So each vertical, which on my dissertation, like there's a reason I tried to split them across, but they were focusing on like each model checking aspect. Like each vertical, it optimizes like the individual aspects of like a typical model checking procedure for design space exploration, and it uniquely impacts several verification scenarios, including like the highly prevalent equivalence checking, which I was very proud of, because I think to be able to make an impact on like equivalence checking, it's hard because it's already like such a well-studied field. And then lastly, like improving state of the art in counterexample guided abstraction for multiple properties. So going forward, there are several possible future directions that can further boost the scalability of model checking. So along the design space reduction vertical, extending the D3 algorithm to other logics, and which could include like metric temporal logic or LTLF, specifically logics for which we can like use model checking to establish LTL satisfiability, or like you can use satisfiability solving by reducing the problem to SAT, or like different models such as Markov processors. It can enable reasoning over like a broader range of systems, and then eventually adding native support for parameters to a model checker can significantly improve the way we actually write model specifications for design spaces, and then also be applicable to other scenarios. So along incremental verification, developing new heuristics that actually generate total orderings in contrast of like the partial orderings which our methods generate for both models and properties based on the graph characteristics of the model is actually very promising. And by graph characteristics, I mean things that we can actually learn about the system by just looking at the state space graph. So it could either be the dominators of the graph, it could be the diameters of the graph, it could be how the strongly connected components connect to each other in a graph and things like that. Like these implicit information which we have for like particular model. And in principle, the way Fuse IC3 works is actually by repairing these clauses which represent reachable states. So we might be able to apply the Fuse IC3 method of like repairing clauses across like different model checking algorithms that also perform clausal model checking, clausal learning. And that includes examples like complementary approximate reachability, or K-liveness, which extends IC3 to like support liveness properties to like improve their overall verification performance. And along the property grouping vertical, so we know that like semantic information reaps the maximum benefit of high affinity group verification. But it is actually impossible to learn semantic information without actually consuming verification resources. So methods to actually learn semantic information from simulation, or either from doing like quick PMC runs before we start the actual verification process, is actually a promising direction which can improve the overall scalability of property grouping, and eventually smarter hashing routines can further optimize and boost the scalability. And lastly, with regards to parallel orchestration, right now our techniques, they are exceptional for like a first run of the design, but in the future we would like to adapt our scheduling techniques to actually learn on the fly based on what information is gathered during the run and how we can actually optimize the way in which a particular verification strategy is running based on what we encounter during a model checking run. And lastly, since parallel verification immensely benefits from incremental solving, exploring this incrementality across different reduction and verification engines is very promising. And I think that would really boost the applicability of the parallel verification in like several industrial model checkers. So this brings us to conclusions. So my entire dissertation was focused on optimizing this design space exploration process for large design spaces using model checking. And it is being achieved by reducing this design space exploration problem to the verification of multiple models and multiple properties. We focus all our contribution along 4 verticals. So there's the vertical of design space reduction, which tries to minimize the number of models and properties checked. There is incremental verification to reuse the information learned across runs. There is property grouping to reap the benefits of checking structurally similar properties together. And then there is the final hammer blow of just using all the techniques that we have, how can we use a parallel verification environment to boost everything? Most of the ideas which are included in the thesis, they are fundamental in the sense that although we are talking about design spaces, they have impact on several hardware and software verification tasks. But I would like to emphasize they have impact on like bit level hardware and software verification tasks, since like most of our property grouping algorithms, they work on like bit level netlist. And as I said, like all the techniques which we have, like they're applicable to equivalence checking, which again, like pretty proud of like doing that. And then like several regression verification technologies and even like product line verification, in which we can end up with like different products in a product line that have to be model checked. And lastly, it gives like the dissertation provides sort of a good mix of theory and practice, in the sense that our combinatorial transition system modeling is a theoretical point of view of how to model a design space, but we actually show how it can be modeled in like a off-the-shelf model checker new SMB, and then everything else, it tries to scale the research from small models to like bigger and bigger models. And several of the techniques which I talked about in my dissertation, they're already in use in like commercial model checkers, and which are being used to run like several millions of properties in a day. So yeah, they actually work. So before I end my talk, I would like to thank everyone that actually made this work in the dissertation possible. And frankly, like I started my PhD almost like 5 years ago, and I wouldn't have thought that a day would come I would like actually give a defense. I'm very proud of that. So firstly, Kristen, thank you for being the best advisor I could ever wish for. I think all the work that I've done, this wouldn't have been possible just without your constant encouragement. And thank you for like presenting me with like the best of the best opportunities to like develop my skills and learn to be like at least a decent researcher. And I'm very fortunate to like have Gianfranco, Sumit, Robin, and Radesh on my PhD committee. And I really appreciate all the regular feedback and guidance over the last few years in terms of all the exams that I've given, the courses I've taken with you, and it really helped my entire defense work actually stay on track. So thank you. And Jason, you have been a phenomenal mentor. Like I met you like 2 years ago, but you have taught me a lot. So while academia, like it taught me like how to do research, you have actually taught me how to scale that research and give me like a different point of view on how I can make more impact by thinking about scalability. And I would also like to thank all my collaborators that on my different papers that made this thesis possible. And I really wish for us to like continue collaborating in the future, and that we can publish more and more papers at like top conferences and venues. Like, I learned a lot from each one of you, so thank you. And lastly, I would like to thank all my family and friends. I have been ignoring you for a lot of years now, but I promise that I'll be more connected going forward. So thank you.
So I've been told the best way to do a round of applause over Zoom is for everyone to turn on your cameras and do jazz hands so that Rohit can put us in gallery view and see the applause. So Rohit, if you want to turn on your gallery view, and everyone can turn on your cameras for a minute, and we can do jazz hands and say thank you for a wonderful dissertation talk.
Thank you.
All right. So we'll open it up to questions from the audience. You had 31 people joining, and so you have a very nice audience for a PhD defense. Congratulations on drawing a large crowd. And do any of our audience have questions for Rohit?